Welcome to my channel. On YouTube, a user's guide to the cosmos, from the Big Bang to galaxies, stars, planets, and moons. Where did it all come from and how does it all fit together? A primer for anyone who has ever looked up at the night sky and wondered.
Billions and billions of galaxies. The universe is so vast, we can't even imagine what those numbers mean. But 14 billion years ago, none of it existed until the Big Bang. The Big Bang is the origin of space and the origin of time itself. We take a journey through space and time, from the beginning to the end of the universe itself. This is our world. Every star, planet, atom, blade of grass, and drop of water is unique. Water is ancient. The hydrogen atoms in this picture were born moments after the Big Bang. Then came everything else. The Big Bang is the defining event of our universe, and everything in it. The secrets of our past, present, and future are all contained within this single point in time. To unlock the secrets of the Big Bang, we have to travel outside of our own solar system and journey beyond even our own galaxy. As we travel into deep space, we're actually seeing into the past and getting closer to being able to witness the dawn of time itself. Passing by the first infant galaxies and stars. We arrive at the moment the universe began and face the biggest questions in all of science. This is the holy grail of physics. We want to know why it banged. We want to know what banged. We want to know what was there before the bang. To get the answers, we've built machines the size of cities to simulate conditions when the universe was created, and space telescopes to peer deep into our past. We are getting close to answering the age-old question, why are we here? Where did we come from? Does the universe, in fact, have a beginning or an end? And if so, what are they like? If we find the answer to that, it would be the ultimate triumph of human reason. We would know the mind of God. The origin of the Big Bang is the greatest mystery of all time. And the more we learn, the deeper the mystery becomes. We like to think that our universe is unique. However, now we're not so sure. Perhaps there is a multiverse of universes. Another possibility is that our Big Bang is just one of many Big Bangs, but it may be one of an infinite number of universes. And there may be other regions in that infinite number of universes where a Big Bang is just happening today. But there's only one universe we're sure of, and understanding this one is hard enough. Since the late 1920s, everything we knew about how our universe works has been turned upside down. It's important to realize how much our picture of the universe has changed in the last century. At the beginning of the 20th century, the conventional wisdom in science was that the universe was static and eternal. In 1929, that all changed. At the Mount Wilson Observatory above Los Angeles, astronomer Edwin Hubble discovered galaxies aren't stuck in one place. Not only are they moving, but they're flying away from Earth at incredible speeds. This was the first real evidence of the Big Bang. All galaxies, on average, are moving away from us, and, stranger still, those that were twice as far away were moving twice as fast. And those that were 3 times as far away were moving 3 times as fast, and so on. Everything was moving away from us. It became known as Hubble's law. His discovery is still the starting point for exploration of the Big Bang. What Hubble convincingly demonstrated, by seeing the motion of those galaxies, is that the universe is expanding. Theoretically, an expanding universe must have started from a single point. By measuring how fast the universe is expanding, astronomers calculated backwards and figured out when it burst into life. People ask the question, how do you know that the universe is 13.7 billion years old? I mean, smarty pants, you weren't there 13.7 billion years ago. Well, when you watch television on videotape, you hit the stop button when you see an explosion, and you can run it backwards and see when it actually took place. The same thing takes place with cosmology. We can run the videotape backwards and then calculate when it all came from a cosmic explosion. You don't have to be an astronomer to look back in time. If you gaze up at the night sky, you're seeing stars that are millions of light years away, meaning it took the light from those stars millions of years to get here. So if you look far enough, you should be able to see the beginning of the universe. Named for the groundbreaking astronomer, the Hubble Space Telescope allows us to look deep into the universe, back in time, and closer to the moment of the Big Bang. But for scientists, winding back the clock to the Big Bang was only the first step. When people first hear about the Big Bang Theory, they say, well, where did it take place? It took place over there. It took place over there. Where did it take place? Actually, it took place everywhere because the universe itself was extremely small at that time. These are only some of the most abstract and difficult concepts there are. So here's a mind bender. What came before the Big Bang? The philosophers in ancient times used to say, how could something arise from nothing? And what's amazing to me is that the laws of physics allow that to happen. And it means that our whole universe, everything we see, everything that matters to us today, could have arisen out of precisely nothing. It's one of the biggest hurdles to understanding the Big Bang. First, you have to buy into the premise that something was created out of nothing. It's impossible to describe the moment of creation in human language. All we know is that, from what may have been nothing, we go to a state of almost infinite density, infinite temperature, and infinite violence. Understanding how nothing turned into something may be the greatest mystery of our universe. But if you understand that, you start to understand the Big Bang, when time and space began, and the great big explosion created everything. At the dawn of time, the universe explodes into existence from absolutely nothing into everything. But everything is actually a single point. Infinitely small, unimaginably hot, a superdense speck of pure energy. The Big Bang was so immense that it brought into existence all of the mass and all of the energy contained in all of the 400 billion galaxies we see in our universe in a region smaller than the size of a single atom. The entire observable universe was a millionth of a billionth of a centimeter across at that time. Everything was compressed into an incredibly hot, dense region. It's not even matter yet, just a raging ball of energy. Was the beginning of the universe and everything in it. Everything was simple. All the forces that we know about today were once and for all. The universe was amorphous. It had no structure. In that instant of creation, all the laws of physics, the very forces that engineer our universe, began to take shape. The first force to emerge was gravity. The fate of the universe, its size, structure, and everything in it, was decided in that moment. Carlos Frank uses this supercomputer to create artificial universes to study how gravity shaped the universe. He gives each one a different amount of gravity. The first one he tried had too little, resulting in, well, nothing. Gravity has saved our universe, for if gravity were weaker than it is, we would have a very boring universe in which everything would be flying apart so fast that there would be no galaxies forming. Next, he programmed a universe with too much gravity. If gravity were stronger than we think it is, again, we'd end up with a failed universe. Everything will end up in black holes. It has to be just so. It has to be just right. Lucky for us, the Big Bang got it just right, the perfect amount of gravity. In the turmoil of forces after gravity emerged, still a fraction of a second after the Big Bang, a shock wave of energy erupted and expanded the universe in all directions at an incredible speed. All of space expanded by an unbelievably large factor in a fraction of a second. We believe that in less than a millionth of 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 a millionth, and for the record, that's faster than the speed of light. But, wait, doesn't that break one of the laws of physics? Even schoolchildren know that you can't go faster than the speed of light. But I say there's a loophole there. You see, nothing can go faster than light, nothing being empty space. Don't be concerned. This idea gives even the best minds in science a headache. But it's critical to understanding the early universe. Scientists think it took less than a millionth of a millionth of a millionth of a second for the universe to expand from the size of an atom to the size of a baseball. That may not sound like much, but it's like a golf ball expanding to the size of the Earth in the same amount of time. That means it was expanding faster than the speed of light. That's quick. So many things were happening so fast in the early universe, because everything was so close together, that we needed a new unit of time to describe things. It's called Planck time. To understand just how short the Planck time is, consider this. There are more units of Planck time in 1 second than all the seconds since the Big Bang. The math is mind-blowing. There are more than 31 million seconds in a year, and it's been 14 billion years since the Big Bang. So multiply 31,556,926 by 14 billion and what you get is a really big number. It's a time scale that's so small that all human intuition goes out the window. If we look at our watches and measure 1 second, we can ask, how many Planck times is that? Well, it is a billion Planck times. So, now the Big Bang is only a few Planck times old, an exploding mass of pure energy expanding faster than the speed of light. In the next few Planck times, the universe as we know it will be born. A fraction of a second after the Big Bang, the universe was so small it could fit in the palm of your hand. But in another tiny fraction of a second, it expands to the size of the Earth. Then, moving faster than the speed of light, it grows larger than our solar system. And it's still just a raging storm of superheated energy. It would be hotter, denser, and more violent than anything that we experience in the universe today. Even the interior of a star is calm and serene by comparison to the violence of the earliest moments of the Big Bang. Temperatures were so hot that even the atoms of your body would disintegrate so hot, in fact, that the atoms would be ripped apart. How hot is it? It's trillions of degrees hot. But as the universe continues to expand, it also begins to cool. Dropping temperatures trigger the next stage in the universe's evolution. The raw energy of the explosion is transformed into tiny subatomic particles. It's the first matter in the universe. This conversion of energy into matter was predicted by Albert Einstein years before anyone started talking about the Big Bang. It's the one scientific equation every school kid knows. There is one very familiar formula. That is, E equals mc squared. Says something about the creation of the universe. It says even if the universe was created just out of pure energy, because energy can be converted to matter and matter to energy, you can get all of the stuff that we see in the universe from this pure energetic event. Einstein's little equation had a big impact. It led to the first nuclear bombs. In a nuclear explosion, a small amount of matter is converted into an enormous amount of energy. As the universe was forming, the exact opposite happened. Pure energy transformed into particles of matter. You don't need to create matter in the beginning. You just need energy. And energy alone can lead to the creation of an entire universe. In just a fraction of a second after the Big Bang, the building blocks of our universe began to take shape. But this first matter is unlike anything we see today. The nature of matter has been very different over the age of the universe. What we now think is normal matter was not at all normal in the earliest moments of the Big Bang. That's because conditions were so extreme. There were no atoms yet. But there were tiny subatomic particles. In the earliest moments of the Big Bang, the universe was so hot and dense that there were great amounts of energy. And so particles were created all the time, and energy and matter were transferred back and forth in this hot, dense soup. That earliest matter was too unstable to start forming the universe as we know it. Think of it like this: imagine rush hour at Grand Central in New York City as that superheated early universe. The commuters racing through the main concourse are subatomic particles. If you look at a large crowd of people, they may appear random. That random, quirky motion is very similar to what was happening in the particles in the universe in the earliest moments of the Big Bang. The extreme temperature of the early universe energizes the subatomic particles. They appeared. They disappeared. They race around at incredible speeds. It's pure chaos. It's like people. If they're excited and running around fast to catch trains at a train station, they'll be moving around quickly. But eventually, they calm down and get slower. In a sense, that's what's been happening to our universe. The particles are moving around very fast. And as the universe cools down, the particles move more slowly and, in some sense, less randomly. As the universe cools, the particles stop changing back into energy. Now there are more and more subatomic particles, but it's still a hot, violent place. All this is happening in fractions of a second, too small to detect. But the Big Bang is moving into a critical stage now, a titanic battle between matter and the one thing that can destroy the universe before it even gets started: antimatter. Everything in the universe is made from matter, from the smallest rock to the largest star. And all the matter there will ever be was created from the pure energy of the Big Bang. Einstein's equation, E equals mc squared, says that energy transforms into matter. But it was just a theory. Today, science is able to test that theory. This is CERN in Switzerland, home to the world's largest machine. It's the size of a city and engineered to recreate the conditions millions of years after the Big Bang. If we want to probe ever smaller scales, paradoxically, we need an ever bigger machine. There's just no other way of doing it, so big machines means small physics, which means early times and, therefore, getting closer and closer to the origin of the universe itself. This monster machine is called a collider. It's designed to take us back to those first fractions of a second after the Big Bang. It's a 12-foot wide concrete-lined circular tunnel 17 miles around. The collider makes tiny particles of matter smash into each other at almost the speed of light. For a split second, those collisions generate turbocharged energy similar to the explosive force of the Big Bang. And then that pure energy briefly transforms into matter. Just like it did nearly 14 billion years ago. But a monster machine needs a monster detector to see these collisions. This detector is 5 stories tall and weighs over 7,000 tons. And 7,000 tons, to give you a sense of perspective, is the weight of the Eiffel Tower. But as big as it is, it can't see the actual particles of new matter. They hang around for just a split second and move so fast it can only record their trails. There's a lot of energy in these particles. They move very, very quickly, and so you need a very large number of detectors in order to be able to map the path of these particles very precisely. So, the detector is so big because you need better resolution. It works exactly the same as a camera. The more pixels you have, the better the picture. It's exactly the same here. We just have a 5-story camera. Scientists hope that it'll reveal just how energy transforms into matter. But not just any matter, the kind of matter that emerged 14 billion years ago at the dawn of time itself. But the dawn of time was a critical moment in the birth of the universe, because pure energy also produced one of the most dangerous things in the universe, antimatter. That's right, antimatter, it's real. Antimatter is the mirror image of ordinary matter. However, matter has one charge, and antimatter has the opposite charge. If there was an anti-me made out of antimatter, that person, in principle, could look exactly like me, same personality quirks, same everything, except, of course, when I decide to shake his hand. At that point, we would both blow ourselves to smithereens in a gigantic nuclear explosion. Matter with a positive charge locks horns with its archenemy, antimatter, with a negative charge. The fate of the universe hangs in the balance of this epic battle. Equal amounts of matter and antimatter will cancel each other out, not good. A universe with equal amounts of matter and antimatter is equivalent to a universe with no matter at all, because the matter and antimatter will annihilate back into pure radiation. And there'll be nothing interesting, no stars and galaxies and people in between. Like in a cosmic game of Risk, the side with the most soldiers wins. The score was very close, but there was a winner. For every billion particles of antimatter, there are 1.5 billion particles of matter. That was the moment of creation. The one extra particle of matter in each little volume survives enough to form all the matter we see in the stars and galaxies today. 1 in a billion might not sound like much, but it's enough to build a universe. We're the leftovers. So, believe it or not, everything you see around you, the atoms of your body, the atoms of the stars, are nothing but leftovers, leaves from this ancient collision between matter and antimatter. Luckily for us, there was enough left over to make all the stars and planets. And the universe is still less than 1 second old. But now it's swarming with tiny, primitive particles. The next stage is assembling those tiny particles into the first atoms. Give or take a couple of Planck times, the universe is nearly a second old and still a very strange place. But matter has won the battle with antimatter. And now it's time to build the universe. It's still extremely hot and expanding incredibly fast. When the universe was a second old, the particles in it were very different from the particles we see today. There were no atoms. Nothing that we recognize in the room around us today yet exists. Now all that is beginning to change. Temperatures continue to cool. And as the primitive particles keep slowing down, they start bonding together to form the atoms of the first elements. The first one to form is hydrogen. Then, over the next 3 minutes, the universe begins to create 2 more elements, helium and lithium. We went from a universe that was infinitely small to a universe that was light years in size. In the first 3 minutes, essentially everything interesting that was going to happen in the universe happened. Well, not quite. If you were there, you couldn't see it. When we look at the night sky, we can see literally billions of years into the past, and we think it's always been that way. Nope, that's not true. 380,000 years after the Big Bang, that's when the universe began to become transparent. But before that, it was milky. There is a milky soup of loose electrons. The young universe has to cool down enough for the electrons to slow down and stick to new atoms. It took a long time for all of the hydrogen, helium, and lithium atoms in the universe to form. Scientists calculate it took 380,000 years for the electrons to slow down enough so that the universe could start mass-producing atoms. When that happens, the milky fog clears. The first light escapes and races across the universe. Nearly 14 billion years later, 2 young scientists in New Jersey pick it up by accident. In 1964, Arno Penzias and Robert Wilson were mapping radio signals across our galaxy. Everywhere they looked, they picked up a strange background hum. They first suspected their equipment. Maybe pigeon droppings on the antenna were causing the strange signal. But after cleaning the antenna, the mysterious hum remained. So much for pigeon droppings. Penzias delivered a talk at Princeton University. And according to lore, one person in the back said, either you have discovered the effects of bird droppings or the creation of the universe. It was indeed the moment of creation, nearly 14 billion years ago, when those first atoms got their electrons. That's the moment when the Milky Cloud clears and the new universe comes into view for the first time. To capture better images of this critical event, NASA launched the Cosmic Background Explorer satellite, or COBE. They pointed it out into space, where it took the temperature of the universe. By measuring differences in temperature across space, they created the first map of our early universe. The images were called the Face of God. We got gorgeous pictures. Baby pictures of the infant universe when it was 380,000 years of age. But there were problems with it. The picture was very fuzzy. The COBE results were simply not good enough. Man, the mission is looking good. Liftoff. So NASA launched an even more advanced satellite, WMAP, the Wilkinson Microwave Anisotropy Probe. In 2001, David Spergel was part of the team looking for a clearer image of the early universe. It was exciting to go to the Cape. It was one of those moments when we were sitting there, watching the rocket go off. I was there with my family. Was very exciting when, within about a day, we were able to get our first signal from the satellite and know that it was working and working properly. This is the most detailed picture of the early universe ever taken, just 380,000 years after the Big Bang. The red and yellow areas are warmer, the blue and green regions cooler. And those temperature differences are clues to the future structure of the universe. You see tiny variations in temperature. Those tiny variations in temperature reflect small variations in density. This area contains more matter. This region has less material. Like a blueprint for the construction of our universe, this image shows us where there's more matter and where there's less. No matter regions will become empty space. Areas with denser matter will become the construction sites of galaxies, stars, and planets. These are the fluctuations that will grow to form galaxies. So if it wasn't for those little density fluctuations, you and I would not be here today. Our universe is now 380,000 years old and trillions of miles across. Clouds of hydrogen and helium gas float through space. It will take another 200 million years before those gases create the first stars. These first stars ignited the universe into what must have been the most amazing fireworks. The universe went from the Dark Ages to an age of splendor when the first stars illuminated the gas and the universe began to glow in majestic fashion. I wish I'd been there. It was like Christmas tree lights turning on. The universe began to light up in all directions, until you formed the beautiful mosaic we now see today. More and more stars light up. 1 billion years after the Big Bang, the first galaxy forms. Over the next 8 billion years, countless more will take shape. Then, about 5 billion years ago, in a quiet corner of one of those galaxies, gravity began to draw in dust and gas. Gradually, they clump together and give birth to a star. Our Sunday 9 billion years after the Big Bang, our tiny solar system springs to life, and with it, planet Earth. Everything there is exists because of the Big Bang, and it's still going on. Our universe is still expanding. But it won't just keep going forever. Our universe had a beginning, and it will also have an end. In the 14 billion years since the Big Bang, galaxies have been created. It is filled with stars, planets, and moons. And the universe has been expanding. The whole time. We've learned space is quite big, at least 150 billion light-years across. The universe may be infinite. It might literally go on forever. The answer is that there doesn't have to be anything, in principle. The universe could be infinite, and there's no outside, or it could be closed on itself. It could be such that if I looked far enough in that direction, I'd see the back of my head. We may never know if the Big Bang produced a universe that goes on forever. But we do know that the Big Bang hasn't stopped yet. The Big Bang is really continuing now. We're continuing to bang, if you want, in the sense that the expansion of the universe is continuing. One of the most astounding discoveries in the last few years has been the realization that our universe is not slowing down, as we once thought, but it's actually speeding up. It's accelerating. It's in a runaway mode. We now believe there's something called dark energy, the energy of nothing, that is pushing the galaxies apart. And is killing the universe. We can't see this destructive force, and we have no idea why it exists. But it could mean the end of everything created in the Big Bang. If dark energy continues to push the universe apart, our Milky Way galaxy could become a lonely outpost. 100 billion years from now, most of our galactic neighbors will be out of sight. Stars will burn out. Galaxies will grow dark. Even atoms will tear apart. The birth of the universe, the Big Bang, was over in a flash. But the death of our universe will take almost forever. That great philosopher of the Western world, Woody Allen, once said eternity is an awful long time, especially toward the end. Figuring out how our universe will end is as dark a mystery as the Big Bang. It could collapse back in on itself, like a balloon when the air is let out. So, would the universe end with a big crunch, a reverse of the Big Bang, or would it end by expanding out and becoming cold and dark? If you wished, would it end in fire or ice? Or with a bang or a whimper? If the universe collapses, it might trigger another Big Bang. Maybe that's already happened, and we're just one in a long line of universes. Personally, I believe in continual genesis, that is, there's a never-ending process whereby universes collide, split apart, and give birth to new universes, perhaps with different laws of physics within each universe. Maybe this isn't the first time it's happened. Maybe it's cyclic, and it goes around and around again, eventually collapsing, and the whole thing will start over again. One universe or many, they all start with a Big Bang. Everything that makes us human, the atoms in our bodies, the jewelry we wear, all the things that lead to the tragedy of life, the beauty, the excitement, love, and everything else, arose because of processes that happened 14 billion years ago. And if we really want to understand ourselves at some fundamental level, we really have to understand the Big Bang. 14 billion years ago, the Big Bang created time and space, our whole vast universe, and everything in it, including us. Some people ask the question, what's in it for me? The Big Bang gave us everything we see around us, the distribution of galaxies and stars. It set into motion the creation of elements that we see in the universe. And even the laws of physics themselves, we think, were born at the instant of creation. Everything started with the Big Bang, one brief moment in time 14 billion years ago that contains the answers to our greatest questions about our past, our present, and our future. Each discovery brings us one step closer to understanding how the universe works.